Okay. Good afternoon, everybody. I hear it's a lot quieter today. Don't know what sort of policy or whatever changed, but both the air filters in the rooms I've taught in today have been off. I guess it's nice for the sound aspects of the lecture today. So today what I want to do is talk to you a bit about air pollution. Now, we don't have a big focus in air quality, air pollution within our environmental program, but I do have a little bit of background and an appreciation for it, given my background was Earth and Atmospheric Science. That degree, when I was pursuing it, I did kind of pursue the water track, but most of my classes, or a lot of the classes, had something to do with air quality, air pollution, and then in grad school I also had an air pollution class as well in an environmental engineering program. So I have a pretty good appreciation for air pollution, and even if you're not going to have too many classes focused directly on it, I wanted to use air pollution as a topic to give you a little bit of exposure as we kind of master some of the basics. You know, we're talking about units and conversions and the different scenarios where that might be important, parts per million type stuff. And so I figured air quality was a good place to kind of do a little bit of both. I'm not, in terms of the goals of the course, air quality and air pollution is not really a major part of the course per se, but just dealing with units, mass, and processes in different media is sort of part of the course. So that's what I'm doing today, and we kind of started this last time talking about this ideal gas law. We had some relation between, and it kind of makes sense if you think about it. You've probably played with balloons, water balloons, helium balloons. You probably encountered some pretty simple cases of air pressure and systems where you might deal with expanding gases or things like that. So you could think the pressure times the volume here. Think like a bike tire has a constrained volume, you increase the pressure. Conceptually, you know you're putting more air into there, so there's more air condensed into a space. It's compressible, right? And you could then say that, okay, well, that the amount that's in there is going to relate to some n, that's the number of molecules of air that's in there, right? That's our moles of air. Could also say it as a mass. You have some constant R, and you have the temperature. Because if you've ever noticed, if you drive when it's very cold, your tire pressures might be a bit lower than you're expecting, and you might have a tire pressure sensor going off because the low temperature means that's a lower volume that air is occupying. Because if you can see if you reduce this side by reducing the temperature, then the pressure times the volume has to decrease. If your volume stayed the same, you have the same size tire, you have lower pressure, right? So there's a lot you can do with this relationship with the ideal gas law, and chances are you've seen that in action, just never quite knew it. So with that, this is kind of where we left off last time, I believe. What I wanted to do is go through this problem with you and kind of prove to ourselves a couple of useful metrics. And when I say useful metrics, what I'm talking about, and by the way, for those online, please let me know, say hi if sound is good and all of that. What I mean by useful metrics is there's a concept called standard temperature and pressure, which this problem introduces, STP. And that's talking about at approximately sea level, which is our standard pressure, and at either 0 degrees Celsius, which is freezing point, or 25 degrees Celsius, which is approximately room temperature. Seems a little cooler today, but it's probably the rain and all. In light of that, we can define, a specific nRT, like if we take 1 mole for n. So if we say we have the PV equals nRT, and we say, okay, well, we're holding T as a standard, R is a constant, and let's just say we'll use n as 1, then we have very stereotypical conditions where we can relate pressure and volume for a given mole of some gas and sort of have a shortcut to dealing with problems involving ideal gases that are at room temperature or at freezing temperature, kind of in environments that we might typically think of as when we're trying to design something. You know, here in Louisiana, we're only a few feet above the sea level, so pretty much we're at standard pressure, 1 atmosphere. Okay, so with that in mind, let's take a look at the problem. It says, find a volume of that 1 mole of an ideal gas would occupy at standard temperature and pressure conditions of 1 atmosphere of pressure and 0 degrees Celsius temperature. Repeat the calculation for 1 atmosphere and 25 degrees Celsius. So there's probably a couple of things we'll need to remember here. First of all, R, that value, go ahead and grab it from the previous slide. And in fact, I'm just going to go ahead and edit the slides. I think that'll be easier. Just give me one moment and I'll put that on there a little nicer for you. Okay. Right, so then we have the ideal gas constant R, that's 0.082, etc. And we have the units there. We notice that in the units that we have temperature in K, so make sure you convert that. Take a moment to do that on your own. Okay. So hopefully that you had a chance to take a look and consider how you might have solved that problem. And it turns out really what we're doing is, just looking at the volume, it's pretty simple. And if we take the volume to the one side, we're really just going to be saying volume equals nRT divided by the pressure. And in this case, we're taking the very simplest cases we can, like I mentioned. And so when we say volume at, let's say, 0 degrees Celsius, that's going to be equal to 1, which is 1 mole, times this R, times this temperature, which is at 0 degrees Celsius, that's going to be 0 plus 273.15. So that'll just simply be 273.15 Kelvin divided by, and here the pressure at standard temperature pressure is 1 atmosphere. And we could write 1 mole over here for the N if we wanted to. So that, then we can check our units with the R here being this number, liters times atmospheres, so the atmospheres will cancel. This is times the temperature, Kelvin, to the -1, so it's basically dividing by Kelvin, divided by mole, so we get rid of the Kelvin and mole. What we're left with is just liters, and liters is valid for volume, and so we're happy. So if we do that, if we plug in those numbers, which I've done in Excel, what we'll see here is for the V at 0, we get 22.41 liters. And the V at 25 degrees Celsius, we get 24 liters, well, 24.465. Okay, so this value here, 22.41, is actually pretty handy. 22.41. And if you end up doing much in the atmospheric realm, you'll probably end up memorizing this because it's just pretty much the same as memorizing this R here, just at a specific temperature. So it's a handy little relationship. What this means is 1 mole of a gas, any ideal gas, occupies 22.4 liters of volume at standard temperature and pressure. What the really neat thing about this is it doesn't matter if this is helium or the heaviest gas that exists. It could be argon, could be hydrogen, whatever gas you're looking at, assuming it's behaving like an ideal gas, which means the particles are just kind of randomly, have random motion and are not like sticking together or anything weird like that. Then at sea level, at freezing point, this is the volume. And another thing that tells us is that we can take a volumetric approach and then know something about the mass or the moles of that gas. So if I were to fill my water bottle with just 2 different gases, and I added a set volume of one gas and then filled up the rest of the space with another, then I know actually something specific about the amount I have in there. And we can do this at different pressures as well. So it's a very powerful tool in the sense of dealing with atmospheric and gas phase problems and stuff like that. So the V at 25, like we said, came out to be 24.465 liters, which makes sense. It's a little larger. Gas expands as you heat it. And so given the same pressure, it will expand, right? Or if you don't let it expand, then it'll just be higher pressure. Okay, so all that in mind, problems relating to ideal gases and their amounts hopefully won't be too intimidating with this ideal gas law. It's pretty simple. It's algebra. It's just recognizing that we can manipulate it in this way. Okay, so here's a, kind of expanding on that. So from that, we know the standard volume there. And another thing we can take a look at is if we have 1 part per million volume of some pollutant, that volume to number / mass relationship gives us a handy way to say, okay, well, if I have 1 ppm by volume of carbon monoxide, then I know that's pretty much the same thing as saying I have 1 mole of carbon monoxide per million moles of air total, whatever gases are composed. So that's handy, and that's a nice connection between parts per million for gas phase pollutants and our nomenclature there. And you can do the same for molecules, right? Because mole is just like saying a dozen. You know, you could have 1 dozen eggs per million, you know, whatever people or something, and you could say the same as just one of those instead of 1 dozen of those, right? So it's the same relationship. Okay, another example here. This one is from our textbook. We have 1 cubic meter sample of air. So a 1 cubic meter sample of air was found to contain 80 micrograms per cubic meter of SO2. So this is sulfite here, or well, this is a sulfur dioxide. The temperature and pressure were 25 degrees Celsius and 103.193 kilopascals when the air sample was taken. The question asks, what is the SO2 concentration in parts per million? One thing I'll remind you here is there's a relationship between the kilopascals and atmospheres. So take a moment, see if you can remember that, or look through your notes. I'll give you that in a second, if not, and see if you can solve this problem. Okay, so this 103.193 was the definition of 1 atmosphere. So that many kilopascals, that's 1 ATM. guys getting stuck anywhere, making progress? How you feeling?
I did something, I don't know if it's right. But I did something.
Okay. All right, so let's take a look. You know, it's silly of me to not bring the textbook or bring the textbook's answer directly, because so I did something too, and I'm not 100% sure I'm right, because I'm just standing here like, should have should have brought that just for my own assurance. Okay, so I went ahead in Excel, and I'll write this up with you, just kind of showing you where I did my calculations. I ended with something that is less than 1 parts per million by volume, so more in the range of parts per billion. I think that measures up. So I'm going to move this aside and kind of write that down into the PowerPoint here. So first thing I was said is like, okay, we've got 80 micrograms of this SO2 here. The molecular weight was given to us. The temperature I took from our previous problem and just simply said that's going to be that 25 degrees plus 273, so that gives us 298.15 Kelvin. I wanted to know the mass of this, sulfur dioxide in terms of grams, so I could more easily convert from grams to moles. So I wanted to know how many moles of this gas, we're assuming this is a gas here, do we have? And so I said, well, the mass you can convert from micrograms to just grams by dividing by 1 million. So that's, I guess you could say 8 times 10 to the minus 4th. I have that. So 80 micrograms. So 8 micrograms, that would be 8 times 10 to the minus 6. So this should be 8 times 10 to the minus 5th. What just happened? Okay. So 8 times 10 to the minus 5th grams. Then we take, then I wanted to know, okay, well, what does that correspond to in terms of the number of moles we have of sulfur dioxide? And so what we can do then is take the 8 times 10 to the minus 5th grams, multiply that, or divide that rather, by the molecular weight, 6.4 or 64.06 grams per mole. So I'm just going to say 1 mole SO2 per 64.06 grams of the SO2. So if we do that, we get a number of moles equal to 1.25, essentially, times 10 to the minus 6 moles. Does that make sense so far? Anyone else go for the moles here? Is that what you got? Okay, good. Okay, so from here, move this aside a little bit. From here, the next thing I wanted to take a look at was essentially the total moles of a gas that occupies 1 cubic meter. If we were dealing with 22.46 liters, then we could directly compare this number of moles to just that 1 mole that we know occupies 22.4 or 24.6 or whatever liters. So that said, sorry, keep this out of the way. Getting myself confused with what you guys can see and what I can see. All right. So that said, I wanted to know total moles in that 1 cubic meter. And what we can do is say, well, we know there's 1,000 liters in a cubic meter. So we'll say we can write that relationship there. We've learned that earlier. Then we can say, okay, well, we also just solved for the amount of liters that 1 mole of a gas occupies, right? So we said at these conditions, at 1 atmosphere, 25 degrees Celsius, we know that an ideal gas occupies that 24.465 liters. So we can say, we can multiply, or I guess say, multiply this by 1 mole per 24.465 liters. So we just use that relationship we learned a moment ago by that example, and we just multiplied it here, or essentially divided it so that our liters are going to cancel, and we'll get moles, some amount of moles per cubic meter. Okay? Then we can compare the amount of moles we have of this SO2 to the total moles that we expect in the cubic meter. And that'll give us our parts per million relationship. So it turns out this is a very a number here. This is 40.87 moles of an ideal gas per cubic meter. So then what we want to do is compare this 1.25 times 10 to the minus 6 moles of the sulfur dioxide to 40 moles total. And just by eyeballing it, we can see that's going to be a pretty small number. In fact, since we're dividing by 40, we know that it's going to be less than 10 to the 6, 10 to the minus 6. So we know it's going to be less than 1 part per million. So all that said, we can say 1.25 times 10 to the minus 6 moles SO2 divided by 40.87 moles total. So this would technically include that little bit that is the SO2 in 1 cubic meter. So all the gas inside that 1 cubic meter, all told, we get a ppm, go ahead and put it over here, parts per million by volume equal to 0.03. So we'll just say 0.03. Now, this number is very small, and what I did was I then multiplied it by 1 million. I'll elaborate on that. Hang on. So let's say this was 0.03 times 10 to the minus 6 moles SO2 per moles total. And because we're talking about parts per million, that million was already factored in, and so we say that's 0.03 parts per million, and it's fair to say that's by volume because we're dealing with ideal gases. Could also describe that as by mass, or by, excuse me, not by mass, by number of moles. Does that make sense? All right. Yeah.
So you divide the like when you divided 1.25 times 10 to the negative 6 by 40.87, you divide that number you get from that by 10 to the negative 6, right?
Yeah, so the question is, once I divide these two here, the 1.25 times 10 to the minus 6 divided by 40.87.
And you take that number and divide it by 10 to the 6.
So that gives, yeah, so this division here gives a fraction. What fraction of the air is SO2? but what we want is more like a percentage. You know, if you do this with a percentage, then you multiply by 100.
Okay.
If you do it by a percentage, except we're not doing per 100, which is percent, we're doing per 1 million, which is parts per million, then we multiply by a million, exactly.
Okay, makes sense.
Because like, yeah, 1 over 99 is, or let's say 1 over 100 would be an easier example. 1 over 100 is 0.01, and what percent of that, you know, doing to percentage, we multiply by 100% is the way we often write it, gives us 1%, right? So it's exactly that process. Good, great question. Okay. Oh, it looks like I do have the answer. Good. Okay. I forgot I did that. So this is what the book showed, a little more condensed there. All right. So another example. Here we have kind of flipping between textbooks here, getting reasonable examples for you. So the US air quality standard for carbon monoxide, based on an 8-hour measurement, is 9 parts per million by volume, ppmv. Express this standard as a percent by volume, as well as in milligrams per cubic meter at 1 atm and 25 degrees Celsius. Okay, so we have a few things here. I'm going to go ahead and write up a couple of the metrics and things we've solved for previously. So our volume we solved for at that standard temperature and pressure for 1 mole. That was 24.465. Get this out of your way. So essentially this, as a problem example, is relating, you're converting ppm to milligrams per cubic meter. So this one is essentially reversing the process from our last problem, where last time we had some amount of micrograms of the pollutant in a cubic meter of air. This time we already know the parts per million by volume, and we want to know, well, what mass does that correspond to? So we really just need to take the inverted approach. So we have 9 parts per million by volume. We know that from kind of what we were doing last time, or you could write it out again, that in every 1,000 liters, which is 1 cubic meter, we could divide that by 24, that value at this temperature divided by a 24.465 liters per mole. That'll give us how many moles are in 1 cubic meter of an ideal gas at 25 degrees Celsius. And turns out that is 40.87 moles. Okay, so with that, we can pretty conveniently convert between this 9 parts per million by volume into moles. So what we can say is this 9 parts per billion by volume, that's the same thing as saying 9 times 10 to the minus 6 is the fraction of our carbon monoxide, CO, the fraction of total, right? So it's 9 times 10 to the minus 6. That is the fraction of the total that is carbon monoxide. Okay, that's the same thing as like saying 6% is 0.06 of total, is the fraction of the total. Okay, so that's just a relationship there, like we did last time, relating those two. So if we take that approach, then we can simply multiply these two together. We know there's a total of 40.87 moles in the system, and some portion of those are going to be the carbon monoxide. So what we can say then is 9 times 10 to the minus 6 multiplied by 40.87 moles is going to give us a number here, should be 3.68 times 10 to the minus 4th moles of carbon monoxide. Okay. From here, we can multiply that by our molecular weight of carbon monoxide. So we have the number of moles, and then we can multiply that by grams per mole and arrive at grams. So we take that 3.68 times 10 to the minus 4th moles of carbon monoxide, multiply that by molecular weight, C and O, that's 12 plus 16 is 28, would be our molecular weight there, times 28 grams per mole of CO. So we'll see the moles will cancel and we'll be left with just grams. And from grams, then we can convert to milligrams. So if we do this multiplication, we'll see that we get one, let's see, just write it this way, 0.0103 grams of carbon monoxide, which, if you convert that to milligrams, would be 10.3. Carbon dioxide per cubic meter. Sorry for the slanty. I've got my Excel sheet in the way, so I'm just sort of slanty up to that. Okay, so this is how I wrote it. There you go. Does that make sense? All right. Okay. So want to go on and talk just more generically about air pollution and air quality. And then I will, in a few minutes, give you a quiz on the oil spill stuff back from the stuff from that first lecture that I just assigned you some reading and then told you we'd talk a little more about. So that's the plan for today. So I'll just go through a little bit here with the air pollution. So we have the National Ambient Air Quality Standards. I don't remember when exactly these have been implemented, but a lot of our EPA-driven regulations really began in the 1970s when EPA was really formed, and there was a few different efforts and sort of some revisions there. And then since then, the different water and air quality acts have been revised based on new understanding or based on recognition of certain needs, discovery of new toxins, things like that. Okay, so here we see a list, and this is pretty sure this is not really exhaustive, and also this is from a book that was published, I think, in 2005 or something like that. So these are probably a little bit dated if they've changed at all. Could certainly look up more modern ones, but one thing you might expect is it's a pretty good representation, and maybe things are slightly lower now if we hold them to a higher standard. So carbon monoxide one, we have an 8-hour standard and a 1-hour standard in terms of really you don't want people exposed to this much, and definitely not more than this in these amount of time. So that 9 ppm that we just looked at for 8-hour, or 35 parts per million for 1 hour. And that's because carbon monoxide essentially fools your blood into thinking that it is oxygen when it is not, and it poisons you because it's taking in the carbon monoxide thinking that it's going to be usable, breathable oxygen. Okay, so that's definitely a hazard, and a particular hazard if you're in a situation where you're got a power outage and you are trying to do some sort of combustion at home in order to keep warm or to cook something. It's important to have carbon monoxide sensors that are battery driven and have batteries, because you want to know it if you're poisoning yourself. There's no other good way to know about carbon monoxide. Incomplete combustion will form carbon monoxide, so you don't want a gasoline generator inside your house ever, things like that. Lead, and this is another one. Now you don't get lead in gas phase, but you will get lead particulate matter, so you don't want lead in your exhaust. We used to have leaded gasoline for anti-knocking properties, something about the way engines run. And so we used to be emitting quite a bit, actually, and basically any level of lead is essentially unsafe. So we don't really want any lead. There is a standard, but it's probably more so to do with our detection limit. Nitrogen dioxide, and there'd probably be similar ones at NO. We often term them NOxes, NOx, for like some number of oxygens in there. NOxes and SOxes, the SOx as well. It's listed here. You'll see those sometimes. Those are irritants, not like the very worst thing, but if you see here, it's kind of atmospheric, respiratory. And a lot of times these things, NOxes and SOxes both, will be involved in photo-driven processes, so photochemical processes where the sunlight hits them and there's some sort of catalytic process and they end up forming more ozone. So up in the upper atmosphere, we're happy to have ozone, and we'll see a kind of a picture of that in a moment. And that's a very good thing, but lower atmosphere where we're breathing, ozone is an irritant. It's a strong oxidant. We don't want to be breathing it, and so we don't want things that are going to create ozone or anything like that. So the nitrogen dioxide, sulfur dioxide, both cause aggravation at high concentrations, and you can see these are ranging sort of different ranges of concentrations. There's another, so ozone as well, like I mentioned. So another type of pollutant, so what all those that I've mentioned so far, except for maybe the lead, are gas phase. We also have particle phase, and these would be particulate matter. We label it by the size of the particulate matter itself. So PM10 or PM2.5, that's really micrometers. So when we're talking about PM10, that's any particles that can be removed by a 10 micrometer filter or thereabouts. Usually there's probably some separation classification where stuff larger that's like dust and we don't count it. Stuff in the range of 10 micrometers can pose a certain type of hazard for just aggravation. Sometimes you might be concerned about other things composing that particle. If you've got diesel exhaust, for example, creating lots of fine particles, well, maybe there's a lot of aromatic hydrocarbons in that particulate matter, and so then that particulate matter itself is somehow more aggravating or toxic to be exposed to. And then PM2.5 is another metric. So if you ever get into the air quality field, these are pretty standard metrics of, okay, what's the PM2.5, what's the PM10? You'll just see this type of readout because these are measured pretty as a standard metric for air quality. Okay, so I wanted to show you altitude profiles. Again, if you get into air quality, these will be a pretty common thing to look at, where you have altitude on the y-axis and then some variable changing on the x-axis. It's kind of a strange way to look at it in a sense, except that it does make sense. You go upwards, that's climbing higher in the sky, right? So if you look at the temperature, it actually varies in kind of an interesting way. Down near the Earth, we're generally warmer. As you get up to 10 kilometers, it drops to be colder. I think that's about, cruising altitude for planes is about 10,000 feet, so that's not nearly 10,000 kilometers. That's probably somewhere around here. So you can eventually get up above the troposphere. Then the temperature ends up warming up a little bit up to the stratopause, and then cooling back down, and eventually you would consider it as space, or near space, and then eventually outer space, whatever. If you look at the ozone concentration, I mentioned that a few minutes ago. Down near the surface of the Earth, we do have a little bit of a spike from all the human and just plant material that gets emitted into the atmosphere, wildfires, volcanoes, all sorts of things that are contributing to photochemical processes that end up producing ozone from oxygen. Certainly we do impact that, and you'll have ozone alerts in heavily smogged areas. But really where it peaks is up in the stratosphere where we want it, where the sun is blasting us with really strong UV, and oxygen and ozone are absorbing that UV and splitting apart, creating new ozone. The trouble, if you've ever heard of like the ozone hole and depletion of the ozone layer, that was all catalyzed by specific molecules that would interrupt that process. And catalytically, each molecule would continuously prevent ozone and form something else, maybe just oxygen. And so it would actually just, one molecule would do a lot of harm until it eventually, that molecule is destroyed somehow. And so normally, that's just a great thing. It's kind of naturally replenishing unless we somehow kill its ability to do so. You could also look at all sorts of other gases, a bunch of NOxes and SOxes, and this is volume fraction instead of, I guess, that micrometers per cubic meter, micrograms per cubic meter. And you see oxygen is pretty stable throughout. Water vapor certainly becomes more dominant, lower. All sorts of things that you could consider. And I'm just showing it to you to have a little bit of a grasp. If we did move away from our one atmosphere, all sorts of things are changing in it. That's a whole field in itself. Okay, just a couple of notes about Plume Dynamics, and this kind of brings us back to mass transport and understanding mass transport. If you see a smokestack, then you might be thinking, oh, where is that going to go? Well, there's a few ways to describe smokestacks, and if you watch them and make a note to observe them when you do see them, there's all sorts of factors about the atmosphere that might affect it. Wind, obviously, but there's also something called an atmospheric boundary layer. I'm not going to get too far into it, and it's been a long time since I learned about it myself. But essentially, it's sort of a pressure differential where you might have a layer of clouds. If the clouds are around, you might see that, and it's lower or higher depending on this boundary layer. Sometimes it's so high you don't worry about it, but sometimes it's pretty low, and it sort of compresses one of these smokestacks so that the plume sort of goes lower and along sort of the bottom. Sometimes it's just windy with not much of that. Other dynamics, pretty harsh wind here. There's a lot of things you might incorporate into an analysis to understand how far this smokestack is going to go until it's a certain level diluted, or just trying to understand where it's going and how concentrated it would be when it gets there. Here's another more complex scheme, kind of visualizing that. You have some starting height, you have some wind speed. You can draw the plume boundaries and all these things, and ultimately you're looking at a concentration profile that's most concentrated kind of in the middle of the stack, and then lower up here, lower down towards the bottom. All sorts of stuff you could look at. We're not really going to deal with all that. I just wanted to introduce you to it and kind of show you a little bit about the things that can affect it, right? Maybe there's, certain weather patterns that are causing pressure differences, in some strange way, and really causing it to be wavy, go everywhere, letting it rise just straight up, all sorts of things. Fairly interesting field there for that. And last thing I'll say is you can note that what's going to happen is you're going to have advection. That's the wind pushing it, right? You're going to have diffusion. That's going to be the random walk of particles in any random direction, and that's going to give you a distribution. That's kind of makes the edges of it fuzzy, right? It's the particle slowly wandering away in random directions. And then if you do have some sort of a turbulent flow like this guy, you might have some dispersion just by that turbulence kicking stuff in random directions. So you'll have, which is, I guess, sort of a subset of advection. So all those things would be considered. And if you're doing some mass balance like that one day, you might also need some sort of photochemical process degrading it or transforming it to really understand where the mass is going. And of course, that dynamic changes a lot if you are daytime versus nighttime. Even it's kind of interesting. You can see profiles like these ones, except they track the time of day, and you'll see pretty significant changes in in air quality as a function of the time of day, based on either the nighttime of no sunlight building up certain concentrations of air constituents, and then suddenly the light comes on and all these photochemical processes start happening, or maybe it's been a full day of it, there's not a lot left and the light is diminishing. That has a certain effect on air pollution as well. Okay, any questions, thoughts about all that? I didn't talk about carbon dioxide. Maybe I will more later. One thing I'll say now is, of course, we're considering it as a potential pollutant in terms of climate-related issues. Now, carbon dioxide is pretty safe in terms of breathing unless you fill your volume of air that you're trying to breathe with just carbon dioxide. You don't want to do that because then you'll suffocate. However, in terms of like a traditional pollutant, it's pretty harmless, so we don't treat it like a traditional pollutant. I mentioned the other day, its concentration in our air is approximately 400 parts per million. So you can think about that in relevance to the metrics we saw. And so the way you might regulate it really depends on, almost everything we regulate typically depends on, okay, this has some health outcome or some direct outcome like that. And so it's going to be more challenging to regulate something that doesn't have such a direct metric, even if there is some concern. So maybe I'll talk more about that later. Tell me if you're interested in that. For now, let's load up Kahoot and answer a few questions here. So please remember to go to kahoot.it. If you do have trouble, if your device is not working or something, just write some answers on a piece of paper. That'll be fine. So enter that game pin and then use your 89 number, no spaces, no dashes, as your nickname there. And if you're watching online, but you're distracted, you should probably come back and participate. So I see 12 people online, about 17 people in here, if I counted right. So we should have a few more people. Perhaps we've got some random viewers, I don't know, if they're bots. It's open to the public, so anybody could come and attend, I suppose. All right, so anyone need another moment to log in? Okay, I think you can join late anyway, the thing here. Okay, we'll go ahead and get started. Okay, so which of the following were not different between the Deepwater and Exxon Valdez oil spills, or the oils themselves? So it looks like a fair bit of you got that, not everybody. So it was essentially each of those were different between the two oil spills. So it made a big difference that the oil quality in the Deepwater Horizon was much lighter. It was a lighter crude, they would call it, and it was more mobile. It was more biodegradable, and essentially they had, they say lighter, what they're talking about is molecules that are, put the cursor here where you can actually see it, it was a lighter composition, meaning rather than mostly, let's say, 14 chain hydrocarbons, it was 10 or something like that. You know, some difference in actual molecular composition. Okay, true or false? Natural processes cleaned more oil than human efforts. We'll say in both cases, or in general in these. A couple seconds. Okay, good. So was true that biological degradation was a really large component of the processes there, and in both cases was really the majority. Now, we did some things to try to help that, especially with the Exxon Valdez, but for the most part, it was biodegradation, natural processes that were occurring, using the oil essentially as food. But of course, if it's too concentrated, you got a big ball of oil, it's only going to be the edges of it that bacteria can get at, because it's probably too toxic for them to be living inside like a glob of oil. So you kind of do need some of the dispersing and things like that. So our human activity did help, especially in the case in the Gulf where we did more dispersion. But it's certainly we were able to remove a fair bit just manually or with pumps or stuff, but really most of the stuff really was biologically driven. Okay, which of the following was not a treatment strategy for the Exxon Valdez spill? I'm sorry, I didn't give enough time for this. I didn't realize that was such a short time. I'll void that question. Sorry about that. A few of you who did answer, a couple of you got it right. So just so don't worry about that. I'll take care of that. The deal was there was a storm basically a day or so after the Exxon Valdez, and so that essentially washed all the oil, dispersed it a bit, but sent it all to the shorelines almost immediately. And so, and it had like 50-mile-an-hour winds, so that was a pretty significant storm. And because of that, they didn't even think or were able to use any sort of dispersants. Whereas in the Deepwater Horizon, they were adding dispersants even down at depth, trying to make sure that partly so that it would disperse before it hit the surface, so that the ships doing cleanup directly above the well and trying to do maintenance on the well would not be at risk of catching fire or being involved in a massive oil slick fire. Not only that, but also, like I mentioned, trying to expand the ability for microbes to eat everything, breaking it apart, dispersing it into smaller pieces was really important. There's some controversy, of course, about, hey, we're adding this other hydrocarbon type of molecule that we've designed to disperse it. How toxic is that? How much are we contributing? So certainly tough questions there, part of that. Okay, and sorry, that was supposed to be at least a minute long and I messed that up. But like I said, I'll remove that question. Okay, which event spilled more oil according to the estimates? so most of you got that, and most of you also thought that the Deepwater Horizon did have more. Some of you had a little bit of the scale off. It was about 20 times more oil, according to estimates. It was something like, I think, what was it, 20 or 40 million liters compared to 140, something like that. It was a significant amount more, but not 100 times more. So the Exxon Valdez actually spilled quite a bit. So that you could have, I'm happy that most of you recognize that the Deepwater Horizon, it really was spilling oil, lots of oil, for a very long time. It was months and months. That was actually the tail end of my first year at grad school, and I ended up having what we call the qualifying exam. A lot of the questions were on the Deepwater Horizon oil spill, and it was really interesting because it really did test every aspect of environmental engineering in some sense. You could talk about all that transport, you could talk about the bioremediation side of it, you could talk about the chemical side, what role of photochemical stuff was going on, oxidation, all of that. Okay, so keep in mind, you'll get most of the credit for this quiz just for participating, so don't be too frustrated if that didn't go so well. I do expect you to read and put effort in if I am substituting a class with a reading assignment. So I hope you see, if you take a look back through them, I hope you learned something with that. That's all I have for you today. I do plan to post a homework for you by next class. So your first homework will be up this week.